Hello everyone. Imagine you're sitting in a train that steadily picks up speed or in a car that brakes smoothly to a stop. In both cases, velocity, acceleration, time, and distance are all connected. But how do we connect them mathematically? That's where the equations of motion come in. These are three powerful equations that link velocity, acceleration, time, and displacement when motion happens in a straight line with uniform acceleration. They're the backbone of problem solving in kinematics, and we'll learn all three today. Let's begin with the first equation. It connects the final velocity of an object with its initial velocity, acceleration, and time. Mathematically, v equals u plus at. Here, u is the initial velocity, v the final velocity, a the acceleration, and t the time taken. If you plot velocity against time, this relation appears as a straight line with slope equal to acceleration. In simple terms, the faster the object accelerates, the steeper the slope, and the quicker the velocity changes. Now, let's ask, how far does the object travel in that time? That's where the second equation comes in. It states s equals ut plus 1 by 2 at squared. The first term, ut, is the distance the object would cover if it moved at its initial speed all the way. The second term, 1 by 2 at squared, is the extra distance gained due to acceleration. Graphically, this comes from the area under the velocity time graph. The rectangle represents ut and the triangle represents half at squared. Together, they give the total displacement. But what if time is not given in the problem? Don't worry, the third equation eliminates time altogether. It is written as v squared equals u squared plus 2as. This equation directly links the final velocity to displacement without time in the picture. It's particularly useful in questions like how long a car needs to stop if brakes are applied, or what speed an object gains after falling a certain distance. All three equations work hand in hand depending on the data you're given. Let's solve one together. A train starts from rest and reaches a velocity of 72 km per hour, that's 20 meters per second, in 5 minutes or 300 seconds. Step 1. Find acceleration using the first equation, a equals open bracket v minus u close bracket divided by t, that's 20 minus 0 over 300, which equals 1 over 15 meters per second squared. Step 2. Find distance using the third equation, s equals v squared minus u squared over 2a, that's 400 over 2 times 1/15th, which comes to 3000 meters or 3 kilometers. So, the train's acceleration is 1 over 15 and the distance traveled is 3 kilometers. Notice how we use two different equations to cross-check the answer. Here's another one. A car accelerates from 18 kilometers per hour, that's 5 meters per second, to 36 kilometers per hour or 10 meters per second in 5 seconds. First, calculate acceleration, equals open bracket v minus u close bracket divided by t, that's 10 minus 5 over 5, giving 1 meter per second squared. Now, displacement using the second equation, s equals ut plus 1 by 2 at squared. That's 5 times 5 plus half times 1 times 25, which is 37.5 meters. So the car's acceleration is 1 meter per second squared, and it covers 37.5 meters in 5 seconds. Acceleration isn't always positive. Braking introduces negative acceleration, also called retardation. Suppose a car comes to rest in 2 seconds under a deceleration of 6 meters per second squared. From the first equation, u equals v minus at, that's 0 minus open bracket minus 6 times to close bracket, which gives 12 meters per second. From the second equation, s equals ut plus 1 by 2 at squared. That's 12 times 2 plus half times minus 6 times 4, which equals 12 meters. So the car covers 12 meters before stopping. A perfect example of why drivers must keep a safe distance between vehicles. So, to wrap up, the first equation, V equals U plus AT, links velocity with time. The second, S equals UT plus half AT squared, gives displacement. The third, V squared equals U squared plus 2AS, ties velocity directly to displacement. Together, they form the complete toolkit for solving motion problems under uniform acceleration. From trains and cars to free-falling objects, these equations explain how motion evolves. Mastering these isn't just about exams, it's about seeing the physics in everyday journeys. I hope today's session made the equations of motion crystal clear for you. In the next class, we'll continue with even more fascinating aspects of motion. Until then, keep practicing and keep questioning the physics around you.